Hello everyone, welcome to my YouTube channel. Today we are building the ultimate VIP lane for your data. It is the engine behind how your computer decides what is urgent and what can wait. Imagine you are in hospital emergency room. A patient with a minor cut arrived at 2 p.m. At 2:05, someone with a heart attack rushes in. Think who gets treated first? Obviously, the heart attack patient. This is not a regular queue, it is a priority queue. And today we are learn about how computer scientists implement this using something called a heap tree. Let's dive in. A priority queue is a special data structure where each element has a priority value. Unlike a regular queue where first in first out rules, in a priority queue the element has highest priority comes out first, regardless of when it was added. Priority queues are everywhere. Your operating system uses them to schedule tasks. System critical processes get priority over their background downloads. Navigation apps uses them in distrust algorithm to find the shortest route. A priority queue supports two main operations. First, enqueue or insert, that add an element with a priority. Second one, dequeue or remove. It is get and remove the highest priority element. But how do we implement efficiently? That's where heaps come in. Let's think about different ways to implement a priority queue. We could use an unsorted array. That insert is fast because just add to the end. But finding the maximum, we would have to check every element. That's order n is slow. What about sorted array? Removing the maximum is instant because it is at the end. But inserting, we would need to find the right position and shift elements. Again, order n. That is also slow. The heap gives us best of both worlds. Both insert and removes are order log n. For 1000 elements, that's only checking about 10 levels instead of all 1000. That's the power of algorithm time. A heap is a special binary tree with one simple rule. Every parent must have higher priority than its children. In a max heap, parents are always greater. In a min heap, parents are always less than its children. Today we will focus on max heap for highest priority first. The second rule is a heap must be complete binary tree. This means every level is completely filled except possibly the last, which filled from right to left, no gaps allowed. This structure is crucial for our efficiency. Here is something beautiful. We don't need pointers. We can store a heap in a simple array. The root is at index 0 for any element at index I. Its left child is at 2 multiply I plus 1 and right child at 2 multiply I plus 2 and parent at I minus 1 over 2. This makes heaps incredibly memory efficient. Let's see how insert operation works at heap priority queues. Let's insert elements and watch the magic happen. We will build a max heap with these priorities 10, 30, 25 and 50. First insert 10. First element becomes the root, that is easy. This is tree represents and this is how array represents. Next insert 30. This is called bubbling up or heapify up. We add 30 at the end, then compare with its parent. 30 is greater than 10. So we swap. The heap priority is restored. This is how array represent and this is how tree represent. You can see both steps before and after. Next, we insert 20. 20 goes to right side of root. Is 20 greater than 30? No, so no swap needed. This is tree and this is array represents. Then after we insert 5. 5 becomes left child of 10. 5 less than 10, so we are good. Insert 50. That is interesting one. Before insert 50, you can see this is the tree represents and this is the array how represents. Let's see what happens after insert 50. Step 1, 50 at the end as right child of 10. Then it's compare with parent 10. 50 is greater than 10, so swap. Then after how represent the tree, you can see step 3 is compare with new parent is 30. 50 greater than 30, so then swap. 50 now placed at the root is called bubble to the root. Notice how 50 traveled from the bottom to the top. It compares with its parent at each level and swap when needed. This is why insert is order log n and the maximum number of swaps equals the tree's head, which is log n. Then now let's see how Dequeue operation works at this. This is called bubbling down or heapify down. We compare the node with both children and swap with the larger one. Why the larger one? Because we need to maintain the max heap property. Parents must be greater than both children. We repeat until the node finds its proper place. Again, order log n time. Now let's remove the maximum priority element. This is where things get interesting. The maximum is always at the root. We remove it, but now we have a hole. Here's the trick. Take the last element is 10 and put it at the root. Now the heap property is broken. 10 is less than its children. Time to fix it. So we have to compare it with children. Which child is larger? 30. 10 less than 30. Swap with larger child. Compare again is children. It has only one child. 10 greater than 5. So done. Heap property is restored. So doing the steps again and again, we can remove the maximum priority element easily. Then let's see real world scenario. Let's manage tasks with priorities. I get task list. I give this task priorities like this. Check email is priority 3. Fix critical bug is priority 10. Attend meeting is priority 5, deploy code is priority 8 and get coffee is priority 1. Then let's see how inserted them. First insert email is priority 3, then insert bug. It is priority 10 is greater than 3. Then insert meeting is 5, not swapping. Then insert deploy priority is 8. It bubbles up with 3. Then insert coffee. It is priority 1, not swapping. So then let's see processing task by removing. Process 1 is remove 10 is fix bug. Then remaining 8, 3, 5 and 1. Process 2, remove 8 is deploy code, remaining 5, 3 and 1. Then remove 5 is meeting, remaining 3 and 1. Then remove email, remaining 1 and then it remove. Notice the order we process task 10, 8, 5, 3 and 1. This is sorted by priority, not by when we inserted them. Bugs fix came out even though email was inserted first. This is power of a priority queue. So I think you have a simple idea on heap tree priority queues. So I will come with next video soon. Until then, stay tuned with me. Thank you so much. Bye.